Sorry about that, guys. I thought I wrote down the reduced row echelon form of this thing, but I didn't, because I'm used to you guys telling me what the answer is before I even get here, right? So the reduced row echelon form of this particular guy, I went through and worked it out, is 1, 0, 2/3, 0, 0, 1, negative 1, 0, 0, 0, 0, 0. Okay. Now we all have to get adjusted to a new paradigm, right? Because I'm so used to you guys just telling me what the answers are, so I need to make sure that I really have these written down so that I don't stop in the middle of the video to try to figure out what the answers are, right? So now that we have this, what's going to be the system? What's the system look like? Put it down here. Okay. And in this case, we have what? A plus 2/3 C equal to 0. Here I have B minus C is equal to 0. So that's my system. I'll put that in a box, a little cloud. And what's my solution look like, right? I'll put the solution here. Just to conserve a little bit of space, I apologize again. Solution. We have that A, B, and C, right? A, B, and C. C is anything it wants to be. We call that T. B is also going to be equal to T, right? A is equal to negative 2/3 T. Negative 2/3 T. Now, can you see what my eigenvector is going to be in this case, right? So for eigenvector for this guy, we'll put it over here. Is that, well, let's see if I can squeeze a little bit more in this spot right here. Bear with me, bear with me. In vector form is A, B, C, all right, equals negative 2/3, 1, 1, times T. Now I can let this be my eigenvector, my fundamental eigenvector, negative 2/3, 1, 1, right? But remember that my eigenvector that I choose to be my fundamental eigenvector could be any scalar multiple. I just need a representative to represent the family of eigenvectors I get, this scalar multiple family, right? So I'm going to make this so that I don't get any fractions, because I hate fractions. So if I can get rid of fractions, I'm going to do that. So I'm going to multiply, I'm going to say that let T equal 3. If T equals 3, then I'm going to get a really nice eigenvector without any fractions, right? So coming over here, I'm going to say for lambda equal to, what do we have here? Lambda equal to 4. If I let T equal 3, right? My eigenvector looks like this. Negative 2, 3, 3. Negative 2, 3, 3. Which is nice, right? No fractions, I like that one. Now, could I have chosen negative 2/3, 1, 1? Yes, I could have. But I don't like fractions, so I got rid of it. You know me. The less fractions I have to deal with, the happier I am. And let's put in our last one. Lambda equal to 2, right? Lambda equal to 2 is our last one. Negative 2. So for lambda equal to negative 2, last one of these guys, if I plug in negative 2 into A minus lambda I, right? This is what I'm going to end up with. I know I just erased A minus lambda I, didn't mean to do that. If I plug negative 2 into A minus lambda I, what I end up with is this. 3, negative 1, negative 1, 0, 3, 3, 0, 3, 3, times the vector A, B, C equal to 0, 0, 0. Again, this matrix is singular, right? So let's do Gaussian elimination. So convert this to a homogeneous matrix. All right. Reduced row echelon form of this. I'll have this one already figured out. Thank goodness. Don't have to go do that again. Here I have 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0. Okay. What's the system look like for this guy, right? What do we have? Let's write it out. Let's write it out, see what we have. Make sure that we know what we're doing. We're careful, we're being super careful, right? A is equal to 0. B plus C is equal to 0. That's my system. What's my solution based off of this system? A, B, C. C can be anything it wants to be. Let's call it T. B is equal to negative T. A is equal to 0. So my vector formula is A, B, C is going to be 0, negative 1, 1. That's T. Okay. So here's my guy. So this has no fractions in it, so I'm dealing with the way it is right now. So I'm going to say my eigenvector, the one that's going to be my foundational fundamental eigenvector, is going to be 0, negative 1, 0, negative 1, 1. So we have lambda equal to, what was it, negative 2, I think. B is equal to 0, negative 1, 1. Does that kind of make sense? Does it? I know you guys can't hear me, but I hope it does make sense how I'm getting these eigenvalues and eigenvectors. Right? I love seeing you guys in person and interacting with you guys to see if you're really catching what I'm saying. But that's not the situation that we are in right now. So we got to do what we have to do. All right. So those are my eigenvalues and my eigenvectors. Right. So these are my eigenvalues and their corresponding eigenvector. So essentially when I multiply A times this vector, it's going to essentially stretch it by 4. If I multiply A times this vector, it's going to stretch it by 2 and flip it. If I multiply A times this vector, then I get back my original vector. Nothing changes. Okay, very good. Very good, very good, very good. Let's continue with the next one. Let's do it, our next example. Let's do a 4 by 4. I know, again, if this is tiring to you guys, this is kind of nice that you can kind of skip ahead to the properties of eigenvalues if you want to. But the 4 by 4 I think has something interesting I want you guys to see. But you can do what you want to do in this particular case, right? This is the power of having a video versus having me in person, right? You can't just kind of fast forward me to the next spot. So it's kind of nice. Here's the next one. Find the, I wanted to talk about eigenspaces, right? So before we do the next example, right? Let's talk about eigenspaces real quick. So let me erase this real quick. I just said I want to talk about eigenspaces next. So let me talk about eigenspaces. So definition. We'll go to that example in just a second. If A is a n by n matrix with an eigenvalue lambda, and eigenvectors B1, B2 to Vk corresponding to lambda, to this particular eigenvalue, then the span, Remember we talked about span is a linear combination of those particular vectors, all possible linear combinations, v1, v2, through v sub k, is called the eigenspace of lambda. It's called the eigenspace of lambda. The eigenspace of lambda, okay? Now, kind of going back to what we just got through doing, right? We just finished working a problem, right, with eigenvalues and eigenvectors, right? So let's talk about the eigenspaces of each one of these guys. The eigenspaces of each one of these guys. So using the previous problem, find the eigenspaces. So if we look at the first one, I can say the eigenspace of lambda equal to 1. I'm going to use a curly E with a 1 here. Eigenspace of 1 is equal to the span. How many eigenvectors does lambda equal 1 have? It only has one eigenvector, so we're just going to say it's going to be the span of 1, 0, 0. This is going to be a line in R3. Remember, it's a line because I have only one direction vector. It's in R3 because we have 3 components. Remember that. Don't forget what you've already learned because we keep coming back to it over and over and over again. The eigenspace of lambda equal to 4 E4 is the span of one single eigenvector in this case, which is going to be negative 2, 3, 3. This is also going to be a line in R3. And the eigenspace of lambda equal to negative 2 is going to be the span of my one single eigenvector I have there, which is going to be 0, negative 1, 1, which is also a line in R3. So these are our eigenspaces, right? Eigenspace. So essentially a line in R3, right, is going to be all linear combinations of 1, 0, 0, which is just going to be a line, and so forth for each one of these guys. Right? We're going to bring this back up again when we do the 4x4 so you can see that we can have more than one eigenvalue for any corresponding we can have more than one eigenvector for any eigenvalue, right? So we can have more than one eigenvector for an eigenvalue. And that's the example we want to do next to kind of give you an idea of what that means. All right, so let's kind of dive in and see. Okay, here's my example. We're finally at the 4x4. Sorry, I had to erase the last one. Here we go, a 4x4 example. Find the eigenvalues, eigenvectors, and eigenspaces of my matrix A, which is given to be, in this case, 4, 0, 0, negative 4, 0, 4, 0, 0, 0, 0, 4, 0. And then I have a row of zeros. So find the eigenvalues and eigenvectors and eigenspaces of this particular example. Again, let's just do what we've done before, right? Be clear. Now, what do I end up with? What do we get? First step, step what? Solve the characteristic equation. For lambda, right? Again, that's setting our determinant of A minus lambda I equals 0. A minus lambda I equals 0. Again, let me just write out what A minus lambda I looks like. That'll be 4 minus lambda, 0, 0, negative 4. 0, 4 minus lambda, 0, 0. 0, 0, 4 minus lambda, 0. 0, 0, 0, negative lambda. Now, when you're using your calculator to find the determinant of A minus lambda I, right, you do not have to use lambda as your variable, right? You can use B, C, D. You can use anything else to replace that, right? Or K. You don't have to find the special character lambda on your calculator to do this, right? Just pick a different variable and use it instead, right? I hope that makes sense, right? You don't have to find lambda. There's nothing special about lambda. This is just a placeholder, right, for our variable, right, our scalar that we're looking for. What is the determinant of this going to be? Well, when you work this out, right, you use your calculator to find the determinant of A minus lambda I. Set equal to 0, right? It should get something that looks similar to this. You might have it expanded out, but whatever the case may be, you should get something that looks like this, kind of like, in this case, we have lambda times 4 minus lambda to the third power equal to 0. So when you solve for lambda, you get that lambda is equal to 0, 4, 4, and 4. Right, that's going to be my solution. Notice I get 4 values because this is a 4 by 4 matrix. Okay, I get 4 eigenvalues, right? Notice that this eigenvalue repeated 3 times, right? So what we say is that since this eigenvalue has repeated 3 times in my characteristic equation, we say that 4 has algebraic multiplicity of 3 because it repeats 3 times. So we say that lambda equal to 4 has algebraic multiplicity of 3. Because we had to do some algebra to be able to figure out what my eigenvalue 4 was, right? And it repeated 4 times, so we had to do some algebra. So it has algebraic multiplicity of 3. Now, what is the algebraic multiplicity of 0 then, right? How many times does 0 repeat, right? Well, it only occurred 1 time, right? So we say that lambda equals 0 has algebraic multiplicity of 1. So lambda equals 0 has algebraic multiplicity of 1. Okay? So lambda equals 4 has algebraic multiplicity of 3, right? It repeats 3 times, or it occurs 3 times. And lambda equals 0 has algebraic multiplicity of 1, okay? So now that we have the eigenvalues, right? Now that we have the eigenvalues, let's find the eigenvectors. Let's find the eigenvectors. Okay? So again, step 2. Solve A minus lambda I times B equal to 0 vector for B, right? Our vectors B. For each lambda, right? I know I have 4 twice. So A minus for B for each. I think you get what I'm trying to say. Right. So I want to solve for B, and each eigenvector B is going to come from an eigenvalue, right? So let's do lambda equal to 0. Lambda equal to 0. Again, I want you to pause the video, and see if you can determine the eigenvalues, the eigenvectors for each one of these eigenvalues. For lambda equal to 0 and lambda equal to 4. See if you can figure them out before I've done them all, right? So I'm going to say pause right now. Okay. Hopefully you pause the video and you've given it your best shot of what the eigenvectors are for lambda equal to 0 and lambda equal to 4. So let's do lambda equal to 0. So wherever we say a lambda and a minus lambda I, we replace it with 0. Guess what? It gives us back our original matrix, which means our original matrix was singular to begin with, which makes perfect sense because we have a row of zeros. A, B, C, D equal to 0, 0, 0, 0. Okay. Now, since this is a single matrix, right, let's write this in, let's do Gauss-Jordan elimination on it. Let me just put this to the side. Let's see if I can squeeze it in here, right here. And here I have 4, 0, 0, negative 4, dot, 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 0. Oh, let me use a different color again. I'll do that in just a second. 0, 4, 0, 0, 0. 0, 0, 4, 0, 0, and a row of zeros. Some of you guys who are thinking about these problems a little bit deeper said, do we really need that last column of zeros? The answer is not necessarily, but it kind of helps us to remember what we're trying to solve for, right? We're doing Gauss-Jordan elimination. I'm going to do reduced row echelon form on that guy, right? And I'm going to get 1, 0, 0, negative 1, 0. 0, 1, 0, 0, 0. 0, 0, 1, 0, 0. 0, 0, 0, 0, 0. So far, so good. From what I could tell, right? So far, so good. System, you gotta be careful. Always be careful. Our system is, what is that? A minus D is equal to 0. This is what I'm seeing, right? I'm seeing A minus D is equal to 0. B is equal to 0, right? And I have that C is equal to 0. This is what I'm seeing. Yeah. So my solution I'm going to see if I can go directly to the matrix, the vector formulas. A, B, C, D, right? B and C are both 0. What is D equal to? Well, D is equal to anything I want it to be, which I can write that as T. I'm going to put the T on the outside. Okay. What is A equal to? Well, A is equal to D. So I can say A is equal to T here. So I get 1, 0, 0, 1, T. So my eigenvector, in this case, is going to be 1, 0, 0, 1. So I'm going to write that down in just a little bit. I'm going to go to the next part. Let's look at lambda equal to 4. But 1, 0, 0, 1, that's a nice eigenvector representative. So I'm just going to use that one. Lambda equal to 4. Okay. Let's plug that one in too. Then I'm going to erase that part over there. So for lambda equal to 4, so wherever I see a lambda, I replace it with 4, so I get 0, 0, 0, negative 4. 0, 0, 0, 0. 0, 0, 0, 0. This is odd. 0, 0, 0, negative 4 times A, B, C, D equal to 0, 0, 0, 0. Okay. Definitely, this is a singular matrix. Reduce row echelon. So let's do Gauss-Jordan elimination on this guy. You can kind of tell what's going to happen here, right? This one's probably not going to surprise any of you guys, what we're going to end up with. But what we have to be careful about is the system and then the corresponding solution. So make sure you didn't mess up in this particular spot. This is a spot that most people mess up in. And we want to make sure that we avoid that if we possibly can. We want to avoid that if we possibly can. Now, hopefully you guys got this to be your matrix that we're going to do Gauss-Jordan elimination on. What is the reduced row echelon form of this? I'm going to erase this now. I'm not going to erase this. So I'll keep this here. Okay. The reduced row echelon form is 0, 0, 0, 1, 0, right? 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Oh, look at that. You're like, Doctor, what does it all mean? What is the meaning of life? It's 42. Oh, or the answer to the meaning of life, I always forget which one it is. One of you guys will tell me for sure. What's my system? Is D equal to 0? Is that my solution? Absolutely not. My solution. This goes with A, B, C, and D. Okay. D has to be 0. But what is A, B, and C? And if you say that A, B, and C is anything I want it to be, then you are absolutely right. So let's use R, S, and T. R, S, and T. Now, what does this look like in vector form? In vector form, if I put it right here, vector form, A, B, C, D, this is going to be R times 1, 0, 0, 0, plus S times 0, 1, 0, 0, plus T times 0, 0, 1, 0. Guess how many eigenvectors I have? I have 3 eigenvectors for this eigenvalue of 4. 3 eigenvectors. I have 3 eigenvectors. Each one of these represents a distinct, linearly independent eigenvector. 1, 2, 3. I have 3 eigenvectors. So if I look at this, all of these guys are my eigenvectors. Three eigenvectors. Now this is strange. Here before, when we were talking about the when we did some algebra to find the eigenvalues, right? We noticed that lambda equal to 4 has algebraic multiplicity of 3 because it occurred 3 times, right? Here we have 3 eigenvectors that occurred when we looked at our eigenvalue of lambda equal to 4. So what we say here, we say that okay, lambda equal to 4 has geometric multiplicity of 3. Geometric multiplicity of 3. Some geometry, right? Because think about it, we can make three-dimensional objects. Three-dimensional objects, multiplicity of 3, right? We can make we're essentially in three-dimensional space, right? We can make cubes in R3, and actually in R4, right? This has lambda equal 4 has geometric multiplicity of 3. What about lambda equal to 0? What multiplicity does it have? Lambda equals 0, what geometric multiplicity does it have? Lambda equal to 0 has geometric multiplicity of 1 because it only has one eigenvector, right? So lambda equals 0 has geometric multiplicity of 1 because it essentially has one foundational eigenvector. Lambda equal to 4 has geometric multiplicity of 3 because it essentially has 3 foundational eigenvectors, right? Corresponding, because I have a different parameter, r, s, and t for each one of those vectors that I have there. So essentially I can make cubic objects in R4. What's my eigenspace then? Let's put it all together. Let's bring together all the things that we have kind of learned here. We have our eigenvalues. We have our eigenvector. We have our eigenspace. Okay. Our eigenvalue, our eigenvector, our eigenspace, right? So if I look at the first one, my eigenvalue, I have lambda equals 0. It only has one foundational eigenvector, which is 1, 0, 0, 1. Okay. It has eigenspace, which is going to be the span of 1, 0, 0, 1. This is going to be a line in R4. Okay. Now the next one we have lambda equal to 4. Okay. Lambda equal to 4 is my other eigenvalue. It has eigenvectors. I don't have to rewrite that. Eigenvectors 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Okay. Those are the eigenvectors. And its eigenspace is going to be the span of those three vectors. It's going to be the span of these three vectors, as what is this going to represent geometrically, right? What shape is this going to be? And this is going to be a 3-space. 3-space. In R4. A 3-space in R4. So this is kind of this object, cubic object in R4, right? A 3-space in R4, if you can imagine that. Very good. We're almost done. I know this is a long video, but we're going to keep going. Let's talk about properties of these eigenvalues and eigenvectors. Erase all this stuff, get it out of the way, give you guys a chance to breathe. Whew. Dr. Wesley, I had to go eat dinner after this last example, and now I'm back after eating dinner, and now I'm ready to talk about properties of eigenvalues and eigenvectors. I had to skip out. I couldn't keep going. Well, welcome back. If you had to leave for a little while and get back with me, let's talk about properties of of eigenvalues and eigenvectors. I'll talk about a complex example next time. I might just skip that for right now until, just because it works the same way and it doesn't really give us any more useful information. So let's give the complex example. It's pretty, I like it, but it's not that big a deal, so I might get rid of it for right now. Keep things simple. As simple as I can make it. Properties of eigenvalues and eigenvectors. Okay. Let's start with the first one. Let A be a n by n matrix with eigenvalues. Lambda 1, lambda 2 through lambda n. Okay? So I have n eigenvalues. Now notice that these eigenvalues could be repeat eigenvalues like we had in that last example where 4 repeated 3 times. But just suppose we just wrote all of them out. We should get n eigenvalues total. They may not be distinct. Then, A, the determinant of A is equal to the product of the eigenvalues. The product of the eigenvalues. B, the trace of A is equal to the sum of the eigenvalues. And that's just weird. Man, you mean that if I know what the eigenvalues are, I know what the determinant and trace are? And I say, yes, the eigenvalues are kind of like the DNA. Well, something like the DNA. Eigenvalues and eigenvectors like the DNA of a matrix, right? So if you know the eigenvalues and the eigenvectors, you essentially know everything you need to know about the matrix. C, the matrix A to the K has eigenvalues. Lambda 1 raised to the power K, lambda 2 raised to the power K, lambda n raised to the power K, if K is an integer. It's an integer. I'm not going to talk about irrational or fractional values of K. And then D, if A is invertible, A is invertible, then A to the -1 has eigenvalues. Lambda 1 to the -1, lambda 2 to the -1, dot, 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 lambda n to the -1. Okay? And so this is kind of an extension of this same idea, but we have to make sure that A is invertible. Here for C, A does not have to be invertible, but if K is negative, then A has to be invertible for C, all right? E, the eigenvectors of A to the K are the same as A. So if I know the eigenvectors of A, then I know the eigenvectors of A to the K. They're the same. They're the same eigenvectors that we had when we found out the eigenvectors of A. Okay? And then finally, F. If A is a triangular matrix, if A is a triangular matrix, then the eigenvalues of A are on the main diagonal. I'm going to write that here so you can see it. So if A is a triangular matrix, then the eigenvalues of A are along the main diagonal. Then the eigenvalues of A are along the main diagonal. Okay. Let's look at example. Now get our bearing here. And I'm going to go back, if you will. I want to go back to the first example that we did, which was that 3 by 3. And if you remember what that is, I have it here, if you don't remember. But the first example of it that we had was that A, for that 3 by 3 was 1, negative 1, negative 1, 0, 1, 3, 0, 3, 1. And if you guys remember from that example, we got that our eigenvalues was lambda equal to 1 and 4 and negative 2. Okay. The eigenvectors, if you guys remember for this particular example, eigenvectors were, let's see here, I have 1, 0, 0, negative 2, 3, 3, 0, negative 1, 1. Okay? So these were the eigenvectors that we got previously. So I'm going to say find the eigenvalues of a to the second, a to the negative 3, a to the 0. B, the eigenvectors of a to the second. And C, what in the world is the determinant of a to the second? Determinant of a to the negative 3. And D, what is the trace of a to the second? And the trace of a to the negative 3. So I want to find the eigenvalues of a to the second, a to the negative 3, and 0. Okay? I want to find the eigenvectors of a to the second. I want to find the determinant of a to the second, determinant a to the negative 3. And I want to find the trace of a to the second and the trace of a to the negative 3. Those are the things I want to do. And guess what? I want to squeeze all of that in this part right here. Do I have enough space to be able to do all these problems? I'm going to squeeze my answers here. This spot right here. It's A. A. There, it's a bigger A. What? So let's think of it. I want you guys to pause. I want you to look at these properties right here. I want to pause. I want you to think about what the answers should be. Okay. Let's see if you're right. You're back with me. Let's look at the eigenvalues of a to the second. What are my eigenvalues going to be in this case? Let's look at it. It's going to be what? 1 squared? 4 squared, and what's the last one? Negative 2 squared. Those answers are going to be lambda equal to 1, 16, and 4. It's going to be the answer to this problem. A to the negative 3. We know that this matrix is invertible. Okay. If you didn't know that, it's easy to tell when we find out what the determinant is. A to the negative 3, that's the same thing as lambda equal to 1 to the negative 3, 4 to the negative 3, negative 2 to the negative 3. What are those going to be? Well, that's going to be, we do that, lambda equal to 1 over, what's that, 64, I think? And then this is 1 over negative 8. And let me put these all in a cloud. What about the eigenvalues of a to the 0? It's going to be lambda is equal to 1 to the 0, 4 to the 0, negative 2 to the 0. And my eigenvalues are all 1, 1, and 1. In this particular case. Did you get that right? I hope you did. Let's look at B. What are the eigenvectors of a squared? Well, they're the same eigenvectors as a, right? So when I write that out, I just have 1, 0, 0, negative 2, 3, 3, 0, negative 1, 1. Same eigenvectors as a. C. What's the determinant of a squared? Well, the determinant of a squared, remember, is just going to be the product of the eigenvalues of a squared. The product of the eigenvalues of a squared. So the determinant of a squared is going to be 1 times 16 times 4, which is going to be 64. What is the determinant of a to the negative 3? Well, that's going to be 1 times 1 over 64 times 1 over negative 8. And I have no idea what that is. What is that? Negative 1 over 2, 3, what's that? 512? If I'm wrong, please forgive me. What's the trace? And this one, I'm definitely not going to add the last one together. Trace of a squared is equal to 1 plus 16 plus 4, because we're going to sum the values of my eigenvalues together. And it's going to give me 21. And then the trace of a to the negative 3, we sum the eigenvalues of a to the negative 3, and I'm not going to do that one because I hate fractions. It's probably not that bad. Some of you guys already did it in your head. You already did the problem. You already figured it out. Oh, okay. Whatever this sum is. Okay. Very good. Almost done. Just a couple more examples. Just 2 more, actually, and then we're done. Hopefully, the camera will continue recording. Two more examples, and then we're done. These are actually in the PowerPoint. I'm going to have to erase this. I apologize. I just don't have enough space. Well, can I erase this? I'm going to erase this instead. Keep these up here, keep the properties up. Except for that last property, which I just erased. Here's the last one. Let A, well, second to the last one, let A be a 2 by 2 matrix where the trace of A equal to 1. And the determinant of A is equal to negative 20. Okay, this is in the PowerPoints. Trace of A is equal to 1, determinant of A is equal to negative 20. Find the eigenvalues of A. Find the eigenvalues of A. Well, I say to myself, I know how to do this. The trace of A is really just the sum of the eigenvalues of A. And the determinant of A is really just the product of the eigenvalues of A. So I can say, okay, lambda 1 plus lambda 2 is equal to 1. Lambda 1 times lambda 2 is equal to negative 20. So essentially what I need to do is I can use my calculator to solve this problem, right? I have this system of equations, or I can just use a little bit of common sense. What two numbers add to 1 but multiply to negative 20? They add to 1 and multiply to negative 20. And the answer to that is lambda 1 being negative 5, or positive 5, and lambda 2 being negative 4. 5 plus negative 4 is 1. 5 times negative 4 is negative 20. Or I can use my calculator to solve for these two things. And the last problem, last one, I promise. I'm going to keep this one simple. For the matrix, A equal to 1, 0, 0, 0, 1, 0, 3, 0, 1, 0, 0, 0, 1, 0, 0, okay? 0, 0, 0, negative 4, 0, 0, 0, 0, 0, 2. Okay, this is my guy. For the matrix 1, 0, 0, what? I don't think I have enough zeros. 1, 0, 0, 0, 1. Right? 0, 3, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, negative 4, 0, 0, 0, 0, 2. Okay. Find the eigenvalues. That's all we're going to do. Find the eigenvalues. Last thing, just find the eigenvalues. What are the eigenvalues of this? Now, if I wanted to, I could find the determinant of A minus lambda I, right? And then find the characteristic equation and solve for it. I could do that. But then I realized something. I said, wait a minute. This is a triangular matrix. This is a triangular matrix. This is a triangular matrix. Since it's a triangular matrix, right? Since this guy's a triangular matrix, that means that my eigenvalues are going to be along the main diagonal here. My eigenvalues are going to be along the main diagonal. What are my eigenvalues going to be in this case? Well, I get lambda is equal to 1, 3, 1, negative 4, and 2. 1, 3, 1, negative 4, and 2. Those are my eigenvalues. I want you guys to notice that 1 has algebraic multiplicity of 2 because it repeats. It occurs twice, right? 1 occurs twice. The other eigenvalues have algebraic multiplicity of 1. Okay. So that's it. I'm going to stop there. That's enough for the day. I know that you guys are probably tired. I'm tired. All right. So we're going to stop there. I hope you guys are doing well, and I will see you at the next lecture.